Hello, welcome back. This is our solution to problem 3 from my spring 2020 final exam. Here we're given three different derivatives to compute, and all of them are going to require us to use the first fundamental theorem of calculus. So before we do these, let's quickly recall what the first fundamental theorem says. So in its sort of most basic form, it says if you take the derivative of a function defined by an integral, so say t goes from some constant c to the variable x, and you're integrating a function f of t with respect to t. Well, okay, when you integrate with respect to t, at the end of the day, you shouldn't have any t's left. But what you will have is this x. So you get a function of x. And so the theorem is that provided f is continuous on an interval that contains c through x, then the derivative is actually going to be f of x. So this is a pretty handy theorem. And you can see we can actually apply this immediately in the very first problem. So we're taking the derivative of an integral from, in this case, our c is 3, up to x. We have some function, and we want to take this derivative. So all we have to do is evaluate the integrand, which is sine of L of t, at x. So sine of ln of x. Wow, that really wasn't that hard. Okay, let's look. Is the second one just as easy? Well, hey, there's a prime out here, right? Okay, that's telling us take a derivative. Oh, now this is interesting. You'll notice here the x and the 7 seem to be in the wrong place, right? So we're supposed to have the x in the upper limit, not the lower one. But that's pretty easy to fix because there's a nice property of integrals which says you can switch these bounds at the cost of putting a negative in front. So this would be the same thing as negative the integral from 7 to x, and then I keep here the exponential of t squared minus t plus 1 dt. And of course, we're still taking a derivative. By the way, a couple notes here. Well, one, this exp, a lot of people haven't seen that before. If you write down something of this form, exp of z, this just means e to the z. This is used to avoid having to write things in the exponents, which may themselves be very complicated. Second thing to note is this prime here has to mean derivative with respect to x. Okay, so again, when you compute this integral with respect to t, all the t's go away, but you will be left with an x. So that's what this derivative has to mean. Okay, well now that we're in this situation where the x is the upper limit, we can just directly use the first fundamental theorem of calculus. So, okay, we keep the negative, right? That can pass outside the derivative. And then we're going to evaluate the integrand, the exponential of, well, we evaluate it when t equals x. So we'll get x squared minus x plus 1. All right, not too shabby. Okay, one more to go. And this one has a little bit of a wrinkle to it. So let's see. Well, we're starting with t equals 1. So, okay, that's a constant on the bottom. And, well, we do have an x on the top, but, oh, there is so much more. So this is a function of x. However, it's composed with another function of x, right? Namely the cosine of the square. So we're going to have to use the chain rule here. Now, sometimes people get a little confused as to why we're using the chain rule. So let me give some names to individual pieces here. Let me call this function like little f. And what I'm going to view, remember this is supposed to be a function of x in the end, but let me view the function where if I just had an x up here, let me give a name to that. So let's say we're going to call AF. That's going to be the integral, and this is a function of x. So this will be the integral from 1 to x. Okay, well, I could write the root, but let me just write the f. Okay, so this is f, that's a function of t dt. Okay, if I want to replace this x by cosine of x squared, I have to do it on both sides. So this would mean AF of cosine of x squared would be the integral from 1 to cosine of x squared f of t dt. All right, so now ignore the right-hand side for a moment and just think, how am I going to take a derivative with respect to x of this function on the left? And the answer is you have to use the chain rule because you're taking a derivative of af, but it is composed with another function of x. So the derivative of af of cosine of x squared is equal to the derivative of af evaluated, so let me take this function and evaluate it at cosine of x squared, times, and this is where the chain rule comes in, the derivative of cosine of x squared. Okay, or we could write it as d dx if we want to keep the notation consistent. All right, now, if we want to compute this derivative of af, we already know how to do that. That's what the fundamental theorem tells us. Right? All we have to do is take the integrand and evaluate it at, well, normally x, but here we'd evaluate it at cosine of x squared. All right, so we can write here the square root of, now our t gets turned into a cosine of x squared. So we have cosine of x squared, and then we're going to raise it to the fourth power. So we raise it to the fourth plus 1 times, now we need to take the derivative of the cosine of x squared. And hey, that's also a chain rule problem. So the derivative of cosine would be negative sine. So it'll be negative sine, okay, of x squared, and then times the derivative of x squared, which is 2x. Okay, so in general, whenever you're using the fundamental theorem of calculus and either the lower or the upper limit has a function of x itself more than just x, right? There's actually something more interesting. Then you're going to proceed as normal, evaluating your t at that function, and then multiplying by the derivative. All right, hope this helps.